Hello, today we're going to cover separable equations. This is section 2.2 from our book. Separable equations is the most straightforward method that we learn in differential equations. It is a method that sometimes will get covered in a Calculus 2 class because it's really derived straight from this idea of we can integrate two sides of an equation. So let's see what a separable equation even is, and then we'll go into what the process is for solving and then go ahead and solve a few problems. So our definition of a separable equation means that the differential equation can be written so that we get some form like dy dx is equal to some function g of x times some function h of y. Now the way that's written, what that's telling me is that g of x and h of y perfectly factor away from each other so that we could maybe divide both sides by the h of y and multiply both sides by the dx to get into this form, the second form, where we have dy over h of y, whatever h of y happens to be, is equal to g of x dx. At this point, once we're in this form, we can go ahead and integrate both sides. The left-hand side would be integrating 1 over h of y dy, and that would be equal to integrating the right-hand side, the g of x, with respect to x. Now, the reason we're able to do this is because in this differential form with the derivatives split up, we already have a differential on each side of the equation. So we're not introducing a differential. We're saying we've already got it. Now let's just integrate both sides. The differential that belongs with each side will tell us what we are integrating with respect to. If those differentials were not there, then when we integrate both sides, it would have to be with respect to the same variable. So that's kind of something we have to keep in mind for future problems, but for now, we know we're taking a dy dx, we're splitting it into its differential form so that we can integrate both sides. Now, this only happens if we have a separable equation. So we have to be able to identify whether we have separable equations or not. So let's look at some examples to see if maybe there's something that we can do for each one of these. So the question is, are the following separable or non-separable equations? And if they are, then go ahead and separate them. So the first problem says dy dx is equal to 2x times y. And that to me is a separable equation where h of x is equal to the 2x and g of y is equal to just y. It doesn't matter which one gets the h or the g. It's just that one is a function of x, one is a function of y. And they're perfectly separated through multiplication, so they can be factored apart from each other. So this is separable. And then the next thing is to go ahead and separate them. So first I will multiply both sides by a dx. I'm going to take my dy over dx equals 2xy. And then I will go ahead and multiply both sides, or the whole thing, with a dx. And then this becomes dy is equal to 2xy dx. And then that y on the right-hand side should not be there. I only want stuff with x on the right-hand side. Anything with a y, I want it on the left-hand side with that dy. So I'll divide both sides by a y, and then I have on the left 1 over y dy is equal to 2x dx. And so now this is totally separated, and we could integrate both sides, but that's not what we're being asked to do here. Right now, we're just identifying separable versus non-separable and then separating if we can. So we're done with this problem. The second problem is dy dx equals sine of the sum of x and y. And so that x plus y is the angle, and we can't distribute a sine across the sum. That's just not correct trigonometry. So we have to recall, how can we rewrite sine of x plus y so that maybe we could separate things? So the note I'm going to pull up, save us the time. I've already looked up what the formula is. Sine of a sum of an angle, so sine of x plus y, can be rewritten as sine of x cosine of y plus sine of y times cosine of x. And there's no way for me to factor that. So, all right, there's nothing in common in either of these. So I cannot factor into a form where I'd have h of x times some g of y, or g of y g of x times some h of y. Again, it doesn't matter which one gets h and which one gets g. The fact is that I cannot factor. And so what that means is I would never be able to have all x stuff on one side and all y stuff on the other side. And so we would say that this is not separable, and then there's nothing more we can do with it. Okay, the other issue with this one, and this is just kind of an aside, pulling from what we learned in the first section of the book about linearity. This problem right here is a nonlinear differential equation because that y is showing up in our quote-unquote g of x. So we should just have a function of x over there, and we don't have that. Y is involved with it, and so we can't do anything with it. It doesn't mean that all nonlinear problems are not solvable to us, but this one in particular is definitely not going to work. Okay, the next one, number 3, I have dy dx is equal to xy plus e to the xy squared. Okay, well, let's see. Maybe I can factor out a y, and then that would leave behind an x plus e to the xy. So there's still a y involved, so I would never be able to get all the y stuff on one side and all the x stuff on the other side. That means this is not separable either. Okay, so this, we cannot factor to a form h of x times g of y. Okay, and so those are kind of nice because we can't do anything with them and we're done. And we move on to the next topic or the next example. Okay, so here, starting now, the next 3 problems will all be separable and we're going to solve them. Okay, so we have dy dx is equal to e raised to the 3x plus 2y. All right, here we need to remember some algebra. The e to the 3x plus e to the 3x plus 2y can be rewritten as e to the 3x times e to the 2y. Remember that if you have the same base, you would add your exponents together. So working from the right to the left, if I was to add the exponents together, I would get what the original differential equation was. So this works. And so this looks like here we have a function of x, h of x, times a function of y. So we should be able to go ahead and separate. The e to the 3x, I'll leave where it is. I'm going to go ahead and start off with multiplying both sides by dx. Okay? When I do that, on the left-hand side, I have dy is equal to e to the 3x times e to the 2y dx. Now I need to get the rest of the y stuff over to the left-hand side, so I can divide by e to the 2y. I get 1 over e to the 2y dy is equal to e to the 3x dx. And now I can, one last thing before I go ahead and put some integral symbols on there, is that 1 over e to the 2y can be rewritten as e to the minus 2y dy. And that's equal to e to the 3x dx. Okay, now I can go ahead and put some integral symbols. Whatever I do to one side, I do to the other. So if I'm integrating on the left, I integrate on the right. And on the left, if I integrate e to the minus 2y, I end up with a negative 1/2 e to the minus 2y plus some c, right? We integrate, we get a constant of integration. This is equal to 1/3 e to the 3x plus some d, right? Another constant of integration. Now, notice that if I have constants on either side, I could move both constants to one side and then call it one number, right? So if I move the c over, then I have d minus c, which is still a constant, and I could just call it c. Okay, so kind of doing that, I've got my minus 1/2 e to the minus 2y is equal to 1/3 e to the 3x plus d minus c. And then I'm going to rename d minus c to just be c. There's no sense carrying around two unknown constants. And so we can save time with each of these problems by simply putting a plus c on the right-hand side. When we integrate both sides, we just put 1 plus c on the right-hand side. Okay, now we need to solve, let's see, let me rewrite this one more time. I have negative 1/2 e to the minus 2y is equal to 1/3 e to the 3x plus c. This right here would be an implicit solution because we have not solved for y. And if WebAssign is asking you for an explicit solution, then we have to solve for y to get an explicit solution. I just want to go over that because this is all brand new. Okay, so the first thing I would do is I would start to isolate that e to the minus 2y by multiplying both sides by a negative 2. And I get e to the minus 2y is equal to a negative 2/3 e to the 3x minus 2c. But minus 2c, I mean, that's still just a constant, right? So I could continue to write that as plus c. Multiplying c by a negative 2 doesn't change the fact that it's just some unknown constant, okay? If I had multiplied by an x, I would leave the x, okay? I would not just say, oh, x doesn't matter. It's a variable, so it very much matters. But multiplying by a constant, it's still a constant, okay? So we'll continue to write it as plus c. And now I want to continue solving for y. So the next thing would be to natural log both sides of the equation. So if I take the natural log of both sides, I have the natural log of e to the minus 2y is equal to the natural log of minus 2/3 e to the 3x plus c. I just rewrote that minus 2c as plus c. Now the natural log of e to the minus 2y, the natural log and the e undo each other and leave minus 2y. On the right-hand side, nothing simplifies. Okay, we have a sum inside of a natural log, so there are no properties that will help us. So it's just simply natural log of negative 2/3 e to the 3x plus c. All right, the last step is to divide by a negative 2, and then y is equal to a negative 1/2 natural log of negative 2/3 e to the 3x plus c. And this is my final explicit solution. I am not saying that one of the solutions is better than the other. I'm saying they are both solutions to our differential equation, but depending on what the instructions say, you might have to do more work once you get an implicit solution and work your way to an explicit solution. So just pay attention to that in the homework. All right, next problem. I have sine of 3x dx plus 2y cosine cubed of 3x dy is equal to 0. So the first thing I'm going to do is I'm going to move the dx term over to the right-hand side and then see if I can move stuff around so that I get all y's on the left, all x's on the right. Okay? First things first, I have 2y cosine cubed of 3x dy is equal to a negative sine of 3x dx. Now the cosine cubed of 3x is over there with the dy. I need to divide both sides by that. So I'm going to get a 2y dy is equal to a negative sine of 3x over a cosine cubed of 3x and then dx. And it looks like everything is fully separated. Now, I'm looking at this sine over cosine cubed. That looks like, let's see, if I was to rewrite that, just notice this. There are two ways to handle this problem on the right-hand side. I could use a u substitution and let u be the cosine of 3x, and then du would be the negative 3 sine of 3x, and we could work through that as a u substitution. But also note that sine of 3x, or I should say negative sine of 3x over cosine cubed of 3x is equal to a negative sine of 3x over a cosine of 3x times a 1 over cosine squared of 3x. And that simplifies to be a negative tangent of 3x secant squared of 3x. And I think this is still going to be a u substitution, but I think we can work with it very well. But, I'm playing around right now to see, like, which u sub might be easier for people, right? Is it easier to do a u substitution with sine and cosine, or is it easier to do a u substitution with tangent and secant? That's something that you kind of have to figure out for yourself. I'm thinking that usually sines and cosines are easier for people because people tend to kind of forget the derivative of tangent or the derivative of secant and the antiderivatives of them as well. So maybe leaving things in terms of sine and cosine is fine. Okay. Now I kind of belabored the point, but my reasoning is that you're going to be working through these problems and you are fresh out of Calc 2, or maybe you took Calculus 3, so you've had a little bit of review on integration methods, but the chances are that these are going to be integrals that you still struggle with a little bit. I would say by the end of this class, you won't struggle with these anymore. You'll get plenty of practice. But for now, this is the second one we're working with this semester, so we want to choose wisely what we're going to do. So I'm going to go ahead and put some integral symbols on my problem the way it's written with sine and cosine. So this method also, I'm just going to finish up my note, also requires u sub. So don't use, or I mean you could use, but I'm not going to use. I'll just say that. So I'm not going to use it. Okay. Now on the left-hand side, when I integrate 2y dy, I just get y squared. And on the right-hand side, I need to do my u substitution. Okay. So let me kind of put my note off to the side, and I am going to label very clearly that I'm doing a u sub, and I'm going to write that u, over here I'll do my u sub, u is equal to cosine of 3x, du is equal to minus 3 sine of 3x dx. There is no minus 3 in this problem. There is a negative sign, but not a 3. So we'll divide both sides by 3, and then 1/3 du will replace negative sine of 3x dx. And so now on my right-hand side, so I'm going to rewrite this. So the left is y squared. On my right-hand side, when I replace all my stuff, I have the integral. The minus sine of 3x dx gives me a 1/3 times, and it looks like in the denominator I replaced the cosine cubed of 3x with just u cubed. So I have 1 over u cubed and a du. Okay? All right, so I'm going to rewrite that one more time. I have the integral of 1/3 u to the minus 3 du. And when I integrate using the power rule, I add to the exponent. Negative 3 plus 1 is negative 2. So I divide by that as well. And I have my 1/3 times a negative 1 over 2 u to the minus 2, and then a plus c. And finally, remember u was cosine of 3x. This is going to be a negative 1/6 times, and then u to the minus 2, I'll write it as 1 over. I'll replace my u with my cosine, that's squared, of 3x, and then a plus c. Okay, one more rewrite and I'm done. Y squared is equal to a negative 1/6 secant squared of 3x plus c. This is good enough. When I see a square, I don't want to take a square root. The reason I don't want to take a square root is because there are 2 square roots. And I don't know which one is the one I really want. I don't know if I want the positive square root or the negative square root. So it's safer if I just leave it as y squared equals. And then like anybody working with this problem, this solution in any application would decide whether they could take the square root or not, and then which one they would want. But we won't make that decision for somebody else, and we'll leave it as y squared equals. Chances are a problem like this in WebAssign, it will not ask you for an explicit solution because it knows that there are actually 2 explicit solutions. Okay? All right, one more problem, and then we'll be done with this section. All right, we need to find an explicit solution for the given initial value problem. So we're seeing some of our vocabulary coming up here. We want an explicit solution, that means y equals. And we have an initial value problem. The initial value is tied to this y of negative 1 is equal to negative 1. Okay? So what that means is after we solve the DE, we use y of negative 1 equals negative 1 to solve for the plus c so that we know what it is. In other words, we don't want a family of solutions. We want the solution to this IVP. Okay? So let's go ahead and get started. We have x squared dy dx is equal to, let me see if I can factor on the right-hand side. The right-hand side is y minus yx. They both have a y in common, so I'll go ahead and factor that out. Y times 1 minus x. That looks good. I can multiply both sides by dx. I get x squared dy is equal to y times 1 minus x dx. I can divide both sides by an x squared and a y. And so I'll write that out, what I'm doing there. So in other words, I'm multiplying by 1 over x squared y. So I want to move 2 things to the opposite sides at the same time. So on the left-hand side, I'm left with 1 over y dy. On the right-hand side, I'm left with 1 minus x over x squared dx. One more rewrite, and then I'll be ready. The left stays the same. 1 over y dy is equal to, on the right, I should split that fraction up, and it becomes 1 over x squared minus 1 over x. And then there's my dx. Okay, we are ready to put the integral symbols on both sides and integrate away. On the left-hand side, the integral or antiderivative of 1 over y is the natural log of the absolute value of y. On the right-hand side, the antiderivative of 1 over x squared, that's the same as the antiderivative of x to the minus 2, which would be x to the minus 1 over negative 1, so a negative 1 over x. Minus the antiderivative of 1 over x is the natural log of the absolute value of x, and then we have a plus c. Okay, I love this problem because it's going to bring up, and it's already kind of bringing up, but it's going to bring up a bunch of algebra stuff with natural logs and exponentials that we really need to review before you're faced with them in a homework problem. So I was told to find an explicit solution. I do not have one yet. I have an implicit solution. I could, at this point, go ahead and apply my initial value to solve for c. That's not a problem. So I'm going to go ahead and do that. Just get it over with. So apply y of negative 1 is equal to negative 1 to find c. So we get the natural log of the absolute value of negative 1 is equal to a negative 1 over negative 1 minus the natural log of the absolute value of negative 1 plus c. The absolute value of negative 1 is positive 1, and the natural log of 1 is 0. So I get 0 is equal to negative 1 over negative 1 is 1. The natural log of the absolute value of negative 1 is 0. And then I have my plus c. So c is equal to negative 1. Okay? Now, I'm going to leave, let's see, how do I want to do this? I kind of went the wrong way. I didn't go the wrong way. What I did was fine. I had meant to solve for y before finding c. I already found c, and that's totally fine. I want to go ahead and I'm going to show you both ways. That's what I'll do. Okay, since it's the last problem, why not? So c is minus 1. That means now we can rewrite natural log of the absolute value of y equals negative 1 over x minus the natural log of the absolute value of x minus 1. Okay, now the big moment, we need to exponentiate both sides. You do not exponentiate individual terms. You exponentiate both sides. One of the most common mistakes to make is to slap an e, put an e base on all four terms, but it doesn't work that way. So we should have e to the natural log of the absolute value of y on the left is equal to e raised to the entire, with the entire right side in the exponent. So e to the minus 1 over x minus natural log of x minus 1. That's the entire exponent, okay? Do not do individual terms. Cannot stress it enough. Now, properties of exponents and natural logs. On the left-hand side, e and the ln, they undo each other and they leave behind y. On the right-hand side, instead of writing this as 1e with triple exponents that are all subtracted, I can rewrite this as 3e bases, each with their own exponent. So that would look like this. E to the negative 1 over x times e to the negative natural log of the absolute value of x times e to the minus 1. And with negative exponents, that means we've got some stuff going on with, we need to write stuff down in the denominator. But first, that e to the minus natural log of x, I would like to use the e and the natural log property and how they undo each other, but the negative sign is in the way. So then I need to remember that a multiplier in front of a natural log is a power for what is inside of the log. So I'm going to rewrite again. Y is equal to e to the negative 1 over x times e to the natural log of the absolute value of x to the minus 1 times e to the minus 1. Okay, now The e and the ln completely undo each other and leave an x to the minus 1. So y is equal to, we'll just go ahead and write it, e to the negative 1 over x times x to the minus 1 times e to the minus 1. And when I rewrite this so that I have all positive exponents, this becomes 1 over e to the 1 over x, x, e. And I might go ahead and rewrite that one more time and say that this is y equals 1 over x e to the 1 over x plus 1. All of that's in the exponent. And that would be the final answer. Okay? Another way to do this, so let's see. This way was find c, then solve for y. And this way over here, what I'm going to do is solve for y, then find c. Just so you can see that both ways work, but there are little nuances for each one. So if I solve for y first, I'm going to exponentiate both sides again. So I get e to the ln of the absolute value of y equals e to the negative 1 over x minus the natural log of x plus c. Okay, so I exponentiate both sides. On the left, I'm left with just y. On the right, I rewrite with 3e bases. I get e to the negative 1 over x, e to the negative ln of the absolute value of x, and e to the c. And this is why I wanted to go in this order originally. That e to the c, e is a constant. It's raised to another constant c. So e to the c is just a constant. Like the whole thing is just a c. And that's weird the first time. Actually, it's probably weird the first 17 times. But it is what it is. It's just a constant. So when I rewrite, I would say y is equal to c e to the negative 1 over x. And then e, I'm going to rewrite this one, to the ln of x to the minus 1. And the e and the ln would undo each other. So y would be c x to the minus 1, e to the minus 1 over x. And rewrite one more time. Y is c over x e to the 1 over x. And then I would find c. So I'd apply y of negative 1 equals negative 1 to find c. So I get negative 1 is equal to c over negative 1 e to the negative 1. I can clear my fraction by multiplying each side by a negative e to the minus 1, and I get a double negative on the left, and just e to the minus 1 is equal to c. Okay, so I plug that in, and then y is equal to e to the minus 1 over x e to the 1 over x. I rewrite the e to the minus 1 so that it's downstairs, and I have 1 over x e to the 1 over x e, which again I rewrite one more time, and it's y is 1 over x e to the 1 over x plus 1, which is exactly what we got when we solved this in the reverse order. Okay, so whether you find c first or solve for y first should not matter. In the end, your answer should be equivalent. There are some situations where they may not look quite the same, but they are equivalent up to some algebraic or trigonometric manipulation. Okay, so just maybe practice both ways and see which one you're most comfortable with. But that's all I have for separable equations. To recall, we would make sure that we can separate. Go ahead and separate with any factoring. Be careful with all your algebra rules. And then we integrate both sides and we solve for y. And as you noticed, there are many algebra rules that do come back at us. So, if you're struggling with any trigonometric things or any natural log or exponential things, make sure that you're getting some help for that. You can reach out to me. You can go online. watch videos about it. There's lots of information on any algebra topics. But good luck.